This lesson is on Faraday's law and how we can use it to help us calculate or work out the EMF or voltage generated in a coil that's moving in a magnetic field. In other words, the voltage created in a generator. But before we actually do that and look at some hard examples, I want to look at what Faraday's law of electromagnetic induction looks like, and we're going to just perhaps play around with it and make sure that we understand what it's actually telling us. So the law is actually called, the full law is Faraday's law of electromagnetic induction. And it looks like this. So I'll try that again. The EMF, which stands for electromotive force, which for all intents and purposes, for our purposes, is the voltage. The voltage created in a conductor or a coil that's moving in a magnetic field is equal to the negative rate of change of flux with respect to time. Now, you have seen a few formulas like this. Probably we need to look at this one more closely than the others that we've seen in the past. So we need to draw a couple of points out of this relationship. And that first point is this: that we'll only get an EMF if the flux is changing. So remember, this is magnetic flux, the flux of the flux created by magnetic field lines. So if there is no change in flux, therefore there will be no EMF, no voltage. So the very first point we need to make is that an EMF will only be induced or created if the magnetic flux through the coil or through the conductor is changing. It has to be changing. So, in other words, if the flux is static and there is no change, therefore then there will be no EMF generated. The second point we need to make is we note also that what determines the EMF is not only whether the flux is changing, but how much it changes with respect to time. In other words, how quickly the flux is changing. So the second point we can draw from this relationship is that if the change in flux occurs over a very short time, a small change in time, that will give us a very big value of the voltage. If it takes a long time to cause the change in flux, then the voltage will be much less. And so the size of the voltage, or the size of the EMF, depends on how quickly the flux is changing. And the third point, which is probably the hardest point to grasp at this stage, is that it is actually equal to the negative rate of change of flux. Now, we're not going to explore that right now, but we will explore it in the next lesson. But at the moment, we just will write a comment about it, is that the EMF is actually related to the negative rate of change of flux. Now, don't worry, that's a little bit confusing at the moment. We will come back and look at that point. Okay, so, and you probably guessed this is a photograph of Michael Faraday, who lived around, was it 1791 to about 1867, something like that. And it was this law that he came up with that summarised how conductors can generate a voltage simply by changing the number of magnetic field lines that are passing across them. And so in our next lesson, we're going to look at some examples of how we can actually calculate this voltage.